In 13-4, we're going to look at tessellations of the plane, tessellations with regular and irregular shapes, and creating tessellations with isometries. A tessellation of a plane is the finding of the plane with repetitions of figures in such a way that no figures overlap and there are no gaps. In the first example, we have multiple reptiles and they cover the plane completely. There are no gaps and they do not overlap each other. This is an example of tessellation. Tessellations with regular polygons are both appealing and interesting because of their simplicity. Here we have a tessellation with squares, and it's simply stacked together from left to right. There are no gaps and each of the squares are of the same size. We can tessellate squares differently as well. We can stack them in a brick type pattern here, and it will still tessellate the plane. There are no gaps and there are no overlaps. We can also tessellate the plane with triangles. In this case, we have equilateral triangles, and the triangles are just stacked in this fashion so that there are no gaps in the tessellation. And if I were to continue the pattern, it will cover the entire plane. The next tessellation is a tessellation with hexagons, and you can see each hexagon is just placed next to each other and stacked on top, and we have a honeycomb pattern created by this tessellation. Which regular polygons can tessellate the plane? To understand this, look at the tessellation using hexagons. Around a vertex of any regular tessellation, we must have an angle sum of 360 degrees. We will take 3 times 120, and that is equal to 360 degrees. Remember, the interior angle of a hexagon is given by 6 minus 2 times 180 degrees divided by 6, or that's equivalent to 720 divided by 6, or an interior angle of 120 degrees. This formula comes from n minus 2 times 180 divided by n, and that will give us the interior angle of a regular polygon. If we have 3 pentagons surrounding the vertex of a tessellation, the sum of the angles around the vertex is 3 times 108 degrees, and that's equal to 324 degrees, and that's less than 360 degrees. We do not have enough pentagons to surround the vertex. So 3 pentagons are not enough to form a tessellation around a vertex. What about 4 pentagons? On the other hand, if we include a 4th pentagon, the sum of the angles around the vertex exceed 360 degrees, so there cannot be a regular tessellation using pentagons. Here's a table that summarizes the interior angle of regular polygons. And so you can see the interior angle of a triangle is 60 degrees, the interior angle of a square is 90 degrees, and the interior angle of a pentagon is 108 degrees, and so on. Now this tells us some things. It is not possible to have tessellations for all of these regular polygons. Since 360 divided by a number greater than 120 is smaller than 3, and the number of sides of a polygon cannot be less than 3, no regular polygon with more than 6 sides can tessellate the plane. And the key phrase here is regular polygon. Polygons that have the same side lengths for all of the sides. Semi-regular tessellations are when more than one type of regular polygon is used and arrangement of these polygons at each vertex is the same. The tessellation is called semi-regular. Although there are only 3 regular tessellations, square, equilateral triangle, and regular hexagon, many tessellations are not regular. One factor that must always be true is that the sum of the measures of the interior angles around a vertex must be equal to 360 degrees. A regular pentagon does not tessellate the plane, however some non-regular pentagons do. Here we have a non-regular pentagon. It does have 5 sides, and it would tessellate the plane in this fashion, we're just going to stack them from top to bottom, and then we'll flip the image over and stack it from left to right. And this would definitely tessellate the plane. There are no gaps and overlaps. The following two tessellations were discovered by Marjorie Rice, and the problem of how many types of pentagons tessellate remained unsolved today. There are infinite possibilities of shapes of pentagons, so there's still discoveries made for tessellations today. So how do we create tessellations with translations? Consider any polygon known to tessellate a plane, such as regular quadrilateral ABCD. On the left side of the figure, draw any shape in the interior of the rectangle B. Cut this shape from the rectangle and slide it to the right by the slide that takes A to B. The resulting shape will tessellate the plane. So we have a quadrilateral here, and we're just going to draw a random shape on one side of this rectangle. We're going to take this image and we're going to place it on the right side of our rectangle, so it creates a translation on the right. Now this image, since it's cut out of the left side, will tessellate because we can stack them side by side and there will be no gaps. So we could do any tessellation with a square by just making an image and then cutting it on the other side.